All right, let's get started. So this is the next video in the series about abstract algebra, and it's all about groups. Indeed, we're going to be talking about groups for quite a while. There's a lot to talk about. And that might be surprising that there's so much to talk about because we're about to introduce the definition, and it's actually remarkably, deceptively simple. But there's still active research in group theory to this day. So we're going to introduce the definition, and maybe you'll be taken aback by the fact that there are only 3 axioms, really, and from them we can deduce a ton of facts. And one reason why we care about groups, we're going to get into a bunch of reasons, but one really important thing about groups is that they provide this unifying framework, because group is a pretty general concept, and that actually allows it to describe a lot of things in mathematics and in nature. But let's not worry too much about applications for now. Let's kind of just focus purely mathematically. So this will be, I'm calling this the second unit of our study, and this is the first real abstract object that we're going to look at. So let's give the definition of a group. And so it is, a group is an ordered pair G dot, where G is a set and dot is a binary operation on G. And if you're not sure what that means, it just means that we take 2 elements in G and dot transforms them into a new element. It is an operation on G satisfying 3 axioms. So we need to satisfy all 3 of these for something to be a group. The first one is that the operation is associative. And by that, we just mean that the value of this triple product is independent of bracketing for all A, B, and C belonging to G. The second axiom is that there is a special element of G called the identity element. There's an element E in G such that for all A in G, A times E equals E times A equals A. So E leaves every other element unchanged under the operation of the group. And the final one is that every element has an inverse under our operation. So for each, let's use the little g. For each element G, there is an element H such that G times H equals H times G equals E. Okay? So basically, to each element corresponds another element, and when you combine these elements under the operation, you get back the identity element, as given in the second axiom. So remember, each of these, if we want to show that something is a group, we just need to verify these 3 axioms. But one thing to note is that these axioms were actually chosen really carefully. And there are not certain properties that maybe you would imagine that a nice set would have. And one of those is commutativity. the operation is not necessarily commutative. And that might sound like it sucks, right? Um, but can we think of something that might be associative that's not commutative? Yeah, we can, of course. One such thing is function composition. So composition of functions, f composed with g of h, we can actually, this is independent of the order of bracketing, but it's not necessarily commutative in general. So that's an example of how we might have something that is associative but not commutative. And indeed, like we will have groups of functions very soon. Um, so, but maybe our group is commutative, and we do have a special name for such a group. So this will just be definition 21. If the operation of a group G dot is commutative, by which we mean G times H equals H times G for all G and H belonging to big G, we say that G dot is a commutative group. Or more commonly, an abelian group. And so this is named after the mathematician Abel, who did some founding work on groups, I believe. And so far we've given two definitions that have to do with groups. And we kind of hinted that function composition has a group structure, maybe. We haven't proven anything about that. But in general, groups are really good at describing a lot of things, and that's why we give it such a broad definition. So, for instance, groups are really good at describing symmetries of the world or of mathematics. And you can actually use it to formulate a lot of quantum mechanics. You can use it. You can use symmetry. You can use groups when you do symmetry methods for differential equations, for instance, and a lot of other stuff. So groups are actually a very general concept that serves to do a lot of unification within mathematics. And I guess like if G is a finite set, we will call this a finite group. And it shouldn't come as a surprise. So let's make a couple of remarks. Number one is that we will often just write G instead of G star, especially if the context is clear. You can see how this would be a lot less of a pain in the butt and a lot less tedious. Another note is that for G times H, we usually just write GH. This shouldn't be too surprising, especially if the context is clear. All right, so let's give a couple of examples of groups. These will be really simple examples. So the first thing to note is that the the rational numbers, the real numbers, and the complex numbers all form groups under addition with, with identity 0. What is the inverse of a number under addition? Well, it's just its negative. Okay, and each of these is abelian. Because, of course, addition is commutative. All right, what about under multiplication? Well, so do the integers form a group under multiplication? Well, think about it for a second. No. So we do have a multiplicative identity, and it's 1. However, we run into a problem because when we think about inverses, what is the inverse of 2? You probably want to say 1/2, but 1/2 isn't an integer. So not every element has an inverse, and indeed only plus or minus 1 actually have an inverse. So the integers do not form a group under multiplication. However, can we form a group from the rational numbers under multiplication? Yes, but we have to be careful, right? Because there's one rational number that doesn't have a multiplicative inverse, and that is 0. So the set of non-zero rational numbers, which we commonly, you might see written as q with this x or times superscript, which denotes the set of non-zero rationals, is a group under multiplication. And similar for the non-zero reals and non-zero complex numbers. Okay, we're not going to prove that, but it should be pretty clear. What's a more interesting example? So far we've only looked at sets of numbers. Let's let GL in R denote the set of n by n matrices with real entries and with an inverse under multiplication. Well, so by definition, each of these matrices is invertible, and we call GL in R the general linear group of order n, of degree n, I believe. So what's the identity? Well, it's just the n by n identity matrix, which is It's an n by n matrix, of course. It has ones on the principal diagonal and zeros for every other entry. Okay. Um, and it may be helpful to recall that a matrix is invertible if and only if it has non-zero determinants. And again, we're just kind of going through all this quickly. If we need this stuff later, we can, of course, review it more. Let's take another example. So I assume most viewers would have had some linear algebra. If not, you can ignore this example. Say V is a vector space over field F. Then V plus is an abelian group. The identity is just the zero vector. And this all follows from the axioms of a vector space. Later on, after we've introduced fields, we will actually consider vector spaces. So you'll get exposure to that, I guess. All right, here's a fun one. For each natural number n, the integers mod n is a group under addition of residue classes, or addition of congruence classes. The identity, of course, is the class containing 0. And we will look at more examples of this soon. Also, so we consider the integers under addition mod n. What about under multiplication mod n? So let's let this denote the set of congruence classes that have an inverse under mod n multiplication. With an inverse under multiplication. Well, so this is a group under multiplication of residue classes. Inverses follow from the fact that we specified that there must be an inverse. And it may be helpful to recall that this A has an inverse under multiplication mod n if and only if A and n are coprime, by which we mean that their GCD is 1. Of course. We'll see many examples of this, and there are a lot of good problems on this. Okay, so we've kind of just stated some simple examples of groups, great, but we haven't really like shown anything cool about groups yet. So let's start with this simple fact. Or this is not a definition. This is a lemma. Lemma 22. Um, and we're going to show that the identity element in a group is unique and that inverses are unique. So if G is a group, then the following two things are true. The identity of G is unique. And for each element of G, the inverse is uniquely determined. All right, so let's go ahead and prove this. So to prove 22.1, suppose that G has two inverses. Let's call them E and F. And these are both identities. I think I said inverses, but I meant identities. Well, so we can compute, so E, well, F is an identity, so this is equal to E times F. Multiplication by F doesn't change the value of E. But hold up, because multiplication by E doesn't change the value of F. So this is just F. So E equals F. So the identity is unique. All right, so to prove part 2, suppose, again, this is a uniqueness proof. Suppose that both B and C are inverses for A. So what this means is that A times B is the identity, and C times A is the identity. Okay, so from here, what do? We want to show that B equals C. So C equals, well, what can we do? We can multiply C by the identity. That's free. C equals C times E. But E is AB. And we can use associativity to re-bracket this. CA times B. But hold up, because CA is just the identity, as we showed here. Or as we stated, we didn't really have to work very hard. So this is just the identity times B, but the identity doesn't change B, so this is just B. So B equals C. And this proves that the identity and inverses are unique in a group. And this isn't like some super crazy thing, but if we couldn't prove a simple property like this from the definition of a group, it's worth noting that we'd probably have to include it in the definition, or include them in the definition. But since we can prove them, and in fact pretty easily, from the definition, it would be redundant to include them. So there would be no need to do this. I think we will prove a couple more things in this video. In fact, let's start proving some basic algebraic properties of groups. This will be lemma 23. So let's let G be a group. then, and for each of these, I'm going to give a cute little mnemonic. Um, Sometimes it's really helpful to have these. So then, um, the inverse of an inverse is the original element. Inverse of an inverse. The second one, um, some people call it the sock-shoes property. And the reason for this is when you wake up in the morning, you put on your socks, and then you put on your shoes before you go out the door. And then when you come back in the evening, you actually take off the shoes first, and then you take off the socks. It would be really challenging to do things in the reverse order. Um, so the inverse of putting on your socks and then your shoes is taking off your shoes and then taking off your socks. So that's a fun way to remember this property. And then the third one, I'm going to introduce a little bit of notation for all A1 up to AN and G. I'm going to use the standard product symbol here. Let's let this product be defined inductively like this. Well, so the claim is the value of this product is independent of the ordering of the bracketing. And this is like a generalized associativity. Okay. So we said a lot, but let's prove these now. So the first one, there's not really anything to prove because you really just read off the definition with the roles of A and A inverse reversed. So just read the definition. Follows from a rereading of the definition with A and A inverse mentally swapped. Second one really isn't too hard to prove. So let's let C denote this inverse. Well, what does this do? So then we can just compute. So the first thing to note is that AB times C equals the identity, of course. And, well, we can multiply on the left by A inverse on both sides. And of course, A inverse times E is just going to be A inverse. And we can use the associativity on the left side to get A inverse times A times BC equals A inverse. But, you know, A inverse times A is just E. So EBC equals A inverse. And of course we can just drop that E because it doesn't change anything. So BC equals A inverse. Now we can do a similar process. We multiply on the left by B inverse. We re-bracket. And this, of course, gives the identity. And we drop the identity to get that C equals B inverse times A inverse. But remember, C is just AB inverse. So we've shown what we wanted to show. We've shown the sock-shoes property. And for part 3, the generalized associativity, I really hate to do this, but I actually don't. I think it's a good exercise on induction. So have fun with that if you want to. I guess it would be a good exercise in induction. Yeah. And I think that's where we will end today. A little bit more than 30 minutes. I think that's pretty good. So we'll continue from here.